If we look at how to find the domain and range from a graph, we're going to look at number 1 here first. So if we look at number 1, we're going to notice that right here we have the x value at -3, and right here we have an x value at +2. So to write the domain in interval notation, we have to write it in a way where we only have -3 and 2 as our values and nothing else, because there's no other values included in the domain. So to do that, we're going to use brackets, because if you remember from last year, brackets indicate that it is included in the domain. So we're going to say bracket -3, and then we're going to use the union symbol with a 2. And so that indicates that we only are including -3 and 2 in our domain and nothing else. And then our range, this arrow right here is showing it's going down forever. It comes up to 2 and then continues right over here and goes up forever. So our range is from -infinity to infinity. And now we want to remember that you always want to put parentheses around infinity symbols. Now if we look at number 2, our domain, we're going from right here at -5 over to 5. So I'm going to start by writing -5 to 5. There's no breaks in the graph, and there's an open circle at -5, so we use a parenthesis because we don't want it included. And there's a closed circle at +5, so we want to use a bracket there to include it. Now our range, if we look at our range, it's going from -2 up to +2. And now even though there's an open circle at -2, there's points over here that are included at the y value of -2. So we're going to include that with a bracket, and it's going to go to +2 where we have values up here that are included, so we use a bracket. Number 3 is an easy one, so this is just strictly -infinity to infinity for both of the domain and the range, because we're going down forever, up forever, which creates the range of -infinity to infinity. Oops, wrong one. And then we're also going, as this is going down forever, it's also going left forever, and as this is going up forever, it's also going right forever. So the domain is also going from -infinity to infinity. If we look here at number 4, we have our domain, and so if you notice, it's going left forever and right forever. So that's going from -infinity to infinity. However, our range, it's only here at the value of y equals 3. And if you notice, since the graph is defined at all of these different values continuously at y equals 3, our range is going to be the set of 3 with brackets to include it. If we go to number 5 here, we have points to represent our relation. And so we're going to represent these points in the domain by using brackets because they're included points, and we're going to use unions to include all of different points. So the first x value that is included is right here at -3. So we're going to do a bracket with -3. Now the next one is over here at -2. There's no values between -3 and -2, so that's why we're going to break from -3 and do a union with -2. We're going to continue to do this. The next one's at 1, so we do a union with 1. Next is at 2 here, so then we do a union with 2. And then the last one's out at 5, so then we do a union with 5. Now the range, we do the same thing, but with the y values this time. So we start at the bottom, so we have -5 down here. And then a union, we go up and we have one here at 0. And then the next one, we have 2 points at the value of y equals 1, but we only need to write that once to represent it since they have the same y value. And the last one is up at y equals 4. Now we're going to talk about finding the domain algebraically. So I'm going to label this for Unit 2A, Day 1 notes, and finding the domain algebraically. Okay, so we're going to go through 3 examples, and just keep in mind that these are just 3 examples, so they're not the only types of functions you could see and have to find the domain of. So example 1, if I give you f of x equals 1 over x squared minus x. Now we want to note that this here is what we call a rational function. And so with a rational function, we have our denominator and it creates a fraction. And we cannot divide by the number of 0, so the denominator cannot equal 0. So we're going to use that information to solve for our domain here. So we're going to take this denominator here of x squared minus x, and we're going to just take it and set it equal to 0 and find what values of x would actually make this denominator be 0, so then we can use the fact that it cannot be 0 to find our domain. So to solve for x here, it's a quadratic equation, and to solve a quadratic equation you need to factor it. In this case here though, there's x in this x squared and an x in the second term, so we're going to greatest common factor out an x, which leaves us with x minus 1, and all of that equals 0. From here, now we have 2 different factors, and so we have the factor of x and the factor of x minus 1, and we're going to take each of those factors and we're going to set them separately equal to 0 because we have 2 values being multiplied to be 0, and one of them has to be 0 in order to get 0 out. So we're going to say, okay, well, x equals 0. Well, on that one, x is solved for, so we're done. And we're going to say x minus 1 equals 0. And to solve for x here, we need to add 1 to each side. And so we get x equals 1. But what we want to keep in mind is that our denominator cannot be 0, and these values make our denominator be 0. So x actually cannot equal 0, and x actually cannot equal 1. So now what we're going to do is we're going to create a number line. And we need to check and see what parts of our number line work for our domain. So we're going to put a mark for 0 and a mark for 1. And then we're going to pick a point less than 0, between 0 and 1, and greater than 1. So I'm going to say negative 1, 1/2, and 2. So if I substitute negative 1 in for x and x squared minus x, we're going to get out, well, negative 1 squared is 1, and 1 minus negative 1 is 2. Well, that does not equal 0, so this one works. We know that 0 cannot be an answer, so I'm going to put an x over that. Then if we take 1/2, well, 1/2 squared is 1/4, and 1/4 minus 1/2 is negative 1/4, so again, that's not 0, so that works. We know that 1 cannot work, so we put an x over that. And then we go to 2. Well, 2 squared is 4, and 4 minus 2 is 2, which is not 0, so that works as well. From here, we can write our final answer of our domain. And so this to the left is starting at negative infinity, going to the right all the way to infinity. So our domain is going from negative infinity to negative 1, not negative 1, negative infinity to 0. And it cannot include 0, so we put a parenthesis, and then we have to union 0 to 1, and then union 1 to infinity. Example 2, if I give you g of x equals the square root of 9 minus x squared. Now we want to make a note here that this is a square root function, and that you cannot take the square root of a negative number, so it's called your radicand. So the radicand is what's under the radical. So your radicand has to be greater than or equal to 0. And so what we're going to do is we're going to take this piece right here that's under the square root, and we're going to say, okay, well, 9 minus x squared has to be greater than or equal to 0. So what we're going to do from here is we're going to say, all right, now let's solve for x. So I'm going to add x squared to each side, which gives me 9 is greater than or equal to x squared. And from here, I'm going to take the square root of each side, which gives me plus or minus 3 is going to be greater than or equal to x. From here, just to double check everything, what we want to do is create a number line again. And we're going to put negative 3 and 3 on it. And so from here, we're going to pick a value less than negative 3 between them and then greater than 3. So I'm going to say negative 4, 0, and 4. And we want to check those values and see, do they hold true to make our radicand be greater than or equal to 0? So if we take negative 4 and substitute in for x, we would get negative 4 squared is 16, and 9 minus 16 is negative, which is not greater than 0. So this does not work. We then go to 0. Well, 0 squared is 0, and 9 minus 0 is 9, which is greater than 0, so this works. And then we do 4. 4 squared is 16, and 9 minus 16 is negative, which is not greater than 0, so this does not work. We can note that it can equal 0, and we know that negative 3 and 3 would make it equal 0, so these points both can work. So that tells us that we can now take and write our domain, which is going to go from negative 3 included, so bracket, all the way to 3 also included. So now we'll go to the third and final example. And so if I give you h of t is equal to t over the square root of t plus 1. Now we're combining the last two types of functions from each example. So we have a rational function which tells us our denominator cannot be 0, but we have a square root in our denominator which tells us that what's under the square root must be positive. So we're going to say, okay, well, this t plus 1 right here, we're going to take that, and we know now that t plus 1 has to be greater than 0. Because we can't take the square root of a negative number, and it cannot equal 0 because it's in the denominator of a fraction. So we're going to solve for t. So subtract 1 from each side. So we end up getting that t is greater than negative 1, and so you can go straight from here to an interval, or if it helps you, you could draw a number line with negative 1 on it. And since it says t is greater than negative 1 and not equal to, that would make an open circle there, and greater than would go this way. And so we can write our interval from here and say that our domain is from negative 1, not included, so a parenthesis, all the way to infinity.